Hey kiddos, today we're going to put some algebra behind some of the conceptual things you're doing. I think a lot of you are going to be much more comfortable with this than the notation that we were playing with earlier. So they're called antiderivatives, which I hope you kind of picked up on last week. Do you remember I gave you a squiggle wiggle? We talked about how if you're finding the area under some rate curve, like let's measure this in chickens per second, and then this axis would be in seconds. And if I'm calculating the area under from A to B, and I'm adding up all my rectangles are going to have an area value of chickens per second times seconds, which just comes out to be chickens. So finding the area under a curve is undoing the rate. So today we're going to do something called antiderivatives. We're going to anti-differentiate. We're going to undo derivatives. So the questions are as straightforward as I have this function. I took a derivative and I got this function. I got a cosine. What did I take the derivative of that gave me cosine? So they're called antiderivatives and they're usually a capital F. So what did I take the derivative of that gave me cosine? Sine. Maybe it was sine, or maybe it was sine plus 7. Because if I take the derivative of the plus 7, I'd get a plus 0 up here, and we would never know. So what we do when we take antiderivatives is we just include this arbitrary constant, this plus c, because there might have been some constant added or subtracted to the end of your expression. So that's really as straightforward as they are, and these are only as hard as your memory is bad. So if you remember all your derivative rules, we're just undoing them. Now, I'm not talking like product rule, chain rule, quotient rule. We'll get to that. But things like, hey, I took a derivative and I got this. What did I take the derivative of? Well, I would need you to be able to see that this is 6 times 1 over 1 plus x squared. So I must have taken the derivative of 6 inverse tangents plus something. That's what this is. So then they can get a little bit more exciting. What if I took the derivatives of something and I got this, that? Now let's do one more. I took the derivative of something and I got that. And it's messy and it's involved. But remember, when you take a derivative, you do one term at a time. So when I do an antiderivative, I'm going to do one term at a time. Don't think it all has to be done in one chunk. So what did I take the derivative of that gave me e to the x? Duh. Now this, think about how these happen. These polynomials happen when you have x raised to a power, you pull the power, and you subtract 1. So if this has already been done, your derivative has already been taken, and you were undoing that, you need to undo those 2 steps. If your step is pull the power, subtract 1, then to undo that, the first thing we're going to do is add 1 to the power. And then instead of pulling it and multiplying by the power, we're going to divide by that power. So the 6 is still here because constants just wait on you until you're done. And then divide by my new power. So you're going to add 1, divide by the new. Add 1, divide by the new. So think of this as x to the 1/2. If I add 1, I'd have x to the 3/2. Divided by 3/2 is the same as multiplied by 2/3. Add 1, divide by the new. Secant squared, do you know it? What did you take the derivative of that gave you secant squared? Tangent plus a constant. That's what antiderivatives are. I can ask you the exact same question using that super fun notation that we did last week. So I could ask you the same question inside of an integral. Last week we started saying, and I'll keep saying, that integrals undo derivatives. Finding the area under a curve when you're taking an integral, you're undoing derivatives. So I could put something inside here like x to the 19th minus 2/5 x to the negative second I don't know, guys. It's Friday. How about a cosine? Remember that your integral notation needs a dx. So like this is your f of x, this is your function, and this is your dx. It always has a dx at the end of your integral. All right, I'm not giving you a start and a stop. That's how we know we need a plus c on this. They're called indefinite integrals. So if I anti-differentiate this, I'm going to add 1, divide by the new, minus, when I add 1 to negative 2, I get negative 1. I still have a 2/5. But now when I divide by the negative 1, that just changes my sign. What did you integrate? Oh, I'm sorry. What did you differentiate that gave you cosine? Well, the derivative of sine is cosine plus c. That's what we're doing. You could get some questions that look kind of complicated. Take solace in that you don't know how to do complicated questions. Like, oops, let me make it a little bit more fun. Like this. Maybe that doesn't look complicated to you. Regardless, you don't know how to do that. All you know how to do is undo the back of a flashcard. If it was a flashcard that you made for your derivative rules, that's all we can do. So this thing, before I can even take its derivative. So right now, if you're thinking, oh, this is a chain rule, I need to pull the power, subtract 1 times the derivative of the inside, you guys are not ready to anti-differentiate chain rules. So make it not a chain rule. Let's multiply this out. We're going to multiply out 2x plus 3 times, x squared times x squared plus 3. And we're going to get x to the 4th plus 6x squared plus 9. And that's what we're going to differentiate. I'm sorry, anti-differentiate instead. So add 1, divide by the new. Add 1, dividing by 3 here is just going to change my coefficient to a 2. And then if I add 1, remember there's like an x to the 0 here. So I'd have an x to the 1 over 1 and a plus c on the end. And that is how you anti-differentiate. Okay, so let me do one more kind. So let me go back to this kind where I'm not writing the integral notation. So, hey, you took the derivative of something and you got something friendly like this. Oh, and by the way, you know this information. Okay, well, what does this allow you to do? Well, now when I go find the antiderivative and I add 1, divide by the new, add 1, divide by the new, and some random constant, I can now go find what my plus c value actually is. So this is our input, this is our output, and now I know that 6 equals 0. I know I'm putting zeros in. It's Friday. Some of you can't think, so I'm helping you. I did it for you. So if c is 6, then I can write my entire antiderivative function with a plus 6. Is it always just what this number is? Where'd it go? Nope, it's not. It just happened to be. It completely depends on your function and your input and your output, so don't think that that's always true. All right, hop into Delta and have a great time.